Welcome to our deep dive. Today we're digging into something huge in AI. It's massive energy use. I mean, it's kind of incredible what AI can do, but wow, the power it draws, especially for training those big models.
It's a serious bottleneck, a stupefying amount of energy, as you said.
Hmm.
And, a lot of that isn't even the calculation itself.
Right, it's moving the data, all those numbers back and forth.
Exactly. Think about GPUs. Powerful? Sure. But they spend so much energy just shuttling those model weights, billions of them sometimes, between the memory chips and the actual processing cores.
Yes.
It's costly.
So the hunt is on for more efficient ways. Which brings us to our source today, an IE Spectrum article about a startup, EnCharge AI, and their potentially new approach.
Yeah, and that's our mission for this dive.
Yeah.
Really understand what's going on. We want to look at the promise of analog AI for saving energy.
Okay.
Why the older analog ideas sort of hit a wall.
Right.
And how this EnCharge approach using capacitors and electrical charge, well, how that might finally crack the problem and give us low-power, accurate AI.
Okay, let's unpack this. So AI needs too much power. Analog AI is meant to fix that. How exactly?
Well, the core idea is pretty elegant, actually. Instead of digital bits, zeros and ones moving everywhere, analog AI uses the physics of electricity directly.
To do the math.
To do the math, yeah. And crucially, it tries to store the AI model's weights right there inside the computing part to stop all that data movement.
Ah, so it avoids the shuttle run between memory and processor.
That's the goal. It uses things like, Ohm's law.
Voltage times conductance equals current.
Exactly. And Kirchhoff's law for summing currents. So you can imagine an array where voltages go in, pass through components whose conductance represents the weights.
Doing the multiplication part.
Right. And the currents just add up naturally. It's computation via physics.
Yeah.
And theoretically, it could be incredibly efficient. The article mentions like thousandths of a trillionth of a joule per operation.
Yeah.
Tiny.
Wow. Okay, so if it's that good, theoretically, why aren't we all using analog AI chips right now? What's the catch?
Yeah, that's the million-dollar question, isn't it? The big problem, the one that's really plagued these efforts, is noise.
Noise. Like electrical interference.
Partly, but also just inherent variability and, well, messiness in the components themselves. The source quotes someone calling the devices often used, like resistive RAM or RRAM, messy things.
Ah, messy things. Not what you want for precise calculations.
Not at all. Imagine trying to set two RRAM cells to the exact same conductance value. You apply the same voltage, same time. You still get slightly different results.
Whoa.
And those values can drift, maybe with temperature or just over time. They're not perfectly stable.
And when you're doing millions of multiplications for an AI network,
Those tiny errors add up. They accumulate. It's like trying to measure a mile by adding up footsteps that are all slightly different lengths. Your final distance is going to be off.
and then you have to convert the final analog current back to digital, right, for the next step.
Exactly. And that conversion step, it adds more noise. So researchers tried all sorts of clever software tricks, tried building better RRAM, but getting the high precision needed for modern AI and the super low power consumption, it's been tough.
The article mentioned a graveyard of failed attempts.
Yeah, Naveen Verma at Princeton apparently mentioned that. It really highlights how many different approaches just haven't quite delivered a practical commercial solution that tackles AI's energy problem effectively. The cumulative error just becomes too much for complex tasks.
Okay, so this is where EnCharge comes in, looking at this history, this graveyard, and deciding to try something different.
Right. They took a step back and thought, maybe the issue isn't just measuring current more accurately. Maybe we should compute with something else entirely.
Something less messy.
Hopefully. They shifted to computing based on the amount of electrical charge stored.
Okay, how does that work? What's the physics there?
Instead of Ohm's law for current, they used the relationship. Charge equals capacitance times voltage. So the core component for multiplication becomes the capacitor.
Capacitors. Why are they better? Less noisy.
That's the key insight they're banking on. A capacitor's value, its capacitance, depends almost entirely on its physical shape, its geometry, the size of its plates, the space between them.
Things engineers can build very precisely.
Extremely precisely. As the source says, engineers control geometry very, very well in CMOS technologies. That's the standard, mature process for making chips. Unlike RRAM, where material properties can be tricky, capacitor geometry is stable and predictable.
Ah, I see. So it's based on something much more reliable from a manufacturing standpoint?
Exactly. EnCharge builds these precise capacitor arrays right in the copper interconnect layers above the main silicon.
Okay, so walk me through the operation. How does the calculation happen?
So you have digital weights stored nearby. Simple logic takes input data bits, multiplies them by these weights, and then converts that result into a precise amount of charge delivered to a specific capacitor.
Huh?
Charges from multiple inputs for one neuron just accumulate together on another capacitor.
Sort of like summing the currents, but summing charge instead.
Precisely. And then that final total charge gets measured and converted back to a digital value.
It sounds familiar somehow. Is that basic idea new?
Well, the underlying technique, switched capacitor operation, isn't new at all. It's been used for decades in things like high-precision analog to digital converters, ADCs.
Because it's accurate?
Exactly, because capacitor ratios can be made very accurate and stable. EnCharge's real innovation was figuring out how to adapt and scale this reliable technique for in-memory computing, tailored specifically for the massive parallelism needed in AI.
So bringing it back to the noise problem, the graveyard issue. This charge-based capacitor approach fundamentally avoids that.
That's the claim. By relying on stable, geometry-defined capacitors instead of variable resistive materials and measuring charge instead of noisy currents, they believe they've tackled the noise problem at its physical root. They're leveraging the inherent precision of standard chip manufacturing.
Which brings us to their actual product, the EN100 chip. What are they saying it can do?
The performance claims are pretty eye-catching. They're saying up to 20 times better performance per watt compared to competing chips on various AI tasks.
20 times. Wow. What kind of products are we talking about?
They've got two main cards mentioned.
Yep.
One is a single chip card for PCs, delivering 200 TOPS, that's trillion operations per second,
Okay.
at just 8.25 watts. It's clearly aimed at putting serious AI capability into laptops without killing the battery.
Yeah, 8 watts is definitely laptop territory. And the other one?
A 4-chip card for AI workstations, scaling up to 1,000 TOPS, so quite a bit more muscle for professionals.
And are these real yet? Can people get them?
They're with early access developers now, and they've raised significant funding, over $100 million, with big names like Samsung involved, which suggests some serious backing. More collaborations are planned too.
So, zooming out, what does this mean for you, the listener? Why should you care about this particular chip tech?
I think this gets to the heart of it. The potential here, as Naveen Verma is quoted saying, is that advanced, secure, and personalized AI can run locally without relying on cloud infrastructure.
Ah, bringing AI off the cloud onto your own device.
Exactly. He hopes it will radically expand what you can do with AI. Imagine having truly powerful AI tools for creativity, analysis, assistance running right there on your machine, faster, more privately. That's the promise.
That would be a big shift. But okay, they're not alone in this race, right? It's a crowded field.
Definitely not alone. You've got the big kahuna, Nvidia, always pushing performance with things like their new GB series chips for PCs and workstations. They're the giant.
Sure. Any other startups trying similar things? Low power AI?
Oh, yeah. The article mentions a few. D-Matrix and Axelera are also doing computing in memory, but their approach is digital, using custom SRAM. Then there's Sagents, which is pursuing a more, let's say, traditional analog AI path.
So EnCharge is betting their charge-based analog approach is the winning ticket for efficiency and precision.
That seems to be the bet. They think this specific way of using capacitors and charge gives them a key advantage over both digital in-memory and older analog current-based methods. It's a distinct approach.
Okay, this has been really interesting. We've covered the massive energy cost of AI, the initial promise of analog computing to fix it.
The noise problems that made it so hard creating that graveyard.
Right. And then EnCharge's different path, using capacitors in charge, leveraging manufacturing precision to hopefully overcome that noise barrier with chips like the EN100.
And the potential impact. Bringing powerful, efficient AI directly onto your local devices, maybe changing how we interact with it entirely.
Which leads us perfectly to our final thought for you today. If technologies like this succeed, if powerful AI becomes much cheaper, much more efficient, and truly local on your devices, how does that change things? What kinds of AI applications become possible that just aren't feasible when everything has to go back and forth to a power-hungry cloud? What doors does genuinely local, efficient AI open up for you?